Radioactive decay is the process by which an unstable parent nucleus emits energy in the form of radiation, thereby converting itself to a more stable daughter nucleus. And in the process, there is always some sort of particle emitted. So alpha decay, the first one, is when you have emission of a helium nucleus. Okay, and this is what it would be written as. Now the top number is the mass number and the bottom number is the atomic number, right? So in alpha decay, the starting nucleus emits 2 protons and 2 neutrons, okay? So what happens to its atomic number? Well, Z is the atomic number, so we say Z decreases by 2, okay? And that, of course, changes the element to a different element because the atomic number, the number of protons, dictates what the element is. And then the mass number, which is A, decreases by 4 because there's 2 protons and 2 neutrons lost. So that's alpha decay. So next we have beta plus decay, aka positron emission. And so this is kind of the opposite of beta minus decay, where in this case a proton in the unstable nucleus is converted to a neutron and a positron, E plus, is released or emitted. Okay, so what happens to the atomic number in this case? Well, Z here, okay, is going to be decreasing by 1. So Z minus 1, of course, which changes the identity of the element. And then, of course, the atomic number, or the mass number, does not change again. Okay, and so these beta minus and beta plus, they're kind of the opposites, and it's easy to get them confused because you might think that, well, it's beta plus, so you must be gaining a proton, and beta minus you must be losing a proton. But you need to think about it in terms of what's emitted. Beta minus is emitting an electron while a neutron is becoming a proton, right? Whereas beta plus is emitting a positron, that's where the plus sign comes from, while a proton is converting into a neutron. So a less often talked about form of radioactive decay is electron capture. And this one is kind of similar to beta plus decay, except in this case, an inner shell electron, okay, an inner shell electron actually is captured by the nucleus, hence electron capture, and a proton in that nucleus combines with that electron to form a neutron. So what's happening in terms of the atomic number? Well, ultimately, the proton is being converted to a neutron just like in beta plus decay, so Z decreases by 1. The atomic number decreases by 1. But then, of course, the mass number, again, does not change because there is no net change in the number of protons and neutrons. Okay, so it's very similar to beta plus. And lastly, we have gamma decay, which is my personal favorite. And in this one, you have an unstable nucleus, which simply emits a gamma ray, high energy electromagnetic radiation, without changing the number of protons or neutrons. So essentially, the atomic number Z and the mass number A do not change, okay, unlike all the other ones. And that's why I like this one so much, because it's very easy to memorize. So now let's do a quick practice question applying some of these concepts. So this one says uranium-238 decays to lead-206 through a series of radioactive transformations. How many alpha and beta minus decays occur in the radioactive decay series from uranium-238 to lead-206? And here I've included the atomic symbols for the uranium and the lead, right? And remember, the top number is going to be the mass number, okay, so 238 to 206, and then the bottom number is the atomic number, so from 92 to 82. So let's summarize what's happening in terms of the mass numbers and the atomic numbers, right? So the delta, or the change in the mass number, A, is going to be 238 minus 206, so the final, which is going to be equal to 32. Okay, and then the change in the Z, or the atomic number, is going to be 92 minus 82, which is simply going to be 10. So notice that all the answer choices are some combination of either alpha or of alpha decay and beta minus decay. And what we can do to easily answer this question is recognize that only alpha decay can change the mass number. Beta decay cannot. It doesn't change the mass number at all. So what is the change in mass number, right? Well, it's 32, and remember that alpha decay, right, for each event of an alpha decay, A decreases, the mass number decreases by 4. Okay, so to get 32, you need 8 alpha decays, right? Because we just divide 32, the total change in the mass number, by 4, right? The change in the mass number from one alpha decay situation, and that's going to be equal to 8 alpha decay or decays, right? So for every single alpha decay event, what is the change in the atomic number, right? Well, for 8 alpha decays, remember that there's a decrease in 2 protons every single time, so you would expect to lose Z minus 16 protons, okay, for 8 alpha decays. right? So for one thing, we know that there needs to be 8 alpha decays, so B already has to be correct, okay? But why do we need the 6 beta decays? Well, remember that the net decrease in the atomic number is 10, so there's a net loss of 10 protons, but for the 8 alpha decay events, there's a loss of 16 protons. So how do you get those 6 protons back? Well, you have 6 beta minus decay events, right? Which leads to the atomic number increasing by 6. So then you lose 16 protons due to the alpha decays and gain 6 back from the beta minus decay, and so your net loss is 10 protons. I'd like to take this time to invite you to my live workshop, which I am hosting on Thursday, June the 12th at 8 p.m. EST and 5 p.m. PST. In this workshop, I will be presenting to you in great detail my top 5 strategies for scoring a 516 or above on the MCAT. And these are strategies which I've developed over years of working with students preparing for the MCAT. And they are very helpful, and they could be of assistance to you no matter where you are in your MCAT journey. So I really hope to see you there. Please leave a comment and DM us if you want a link, and you can also check out the link in the linked tree of our TikTok bio. I really hope to see you there.